All planets have or have had fluid layers that are set in motion by huge forces due to their gravitational interactions, to their rotation, and to their cooling. Gaseous clouds, air motions, oceanic currents, all those natural flows are directly observable. But some are not. This is, for instance, the case of the gigantic ocean of liquid iron enclosed in the Earth's core 3,000 kilometers below our feet. Visible or hidden fluids, our team aims to understand their mysterious motions and their consequences. Core fluid motions are partly responsible for the thermal and orbital evolution of our planet. They are also responsible for the existence of a fundamental phenomenon, the magnetic field. Without a magnetic field, no life would be possible on Earth. It protects us from high-energy particles enclosed in solar winds and from cosmic radiations. But how is the magnetic field generated on Earth and on some other planets? In 1919, the physicist Joseph Larmor set the theoretical basis of a self-sustained dynamo. According to this model, motions of a conductive fluid are capable of creating an electric current that generates and amplifies a magnetic field. This is the case of the liquid iron moving in the core of telluric planets. But many aspects of this dynamo mechanism have yet to be explored. The Fludyco project has been designed to go beyond the current limits of our knowledge. We have therefore developed an original approach consisting of studying separately three essential phenomena. The core formation by accretion to quantify the initial thermochemical state of planets, the core convection to understand the flows and the magnetic field possibly created by the cooling of planets. And the impact of rotation to understand how gravitational interactions between planets disturb their rotational motion and influence flows in their core. Three different experiments for three phenomena, because it is still impossible to study the dynamics of planetary cores and magnetic fields as a whole. The multi-physics processes at work are too complex. To carry out this research, we combine the advantages of two methods. Laboratory experiments in the most extreme conditions over long periods. Numerical simulations which give us access to all the variables, but over limited time or within a range of parameters, even using the most powerful computers. During the last 2 years, thanks to this multi-method approach, we've already obtained significant results. The first visualization of the iron rain that occurred during the core formation 4.5 billion years ago. The realization of the first models taking into account simultaneously the turbulent convection and the presence of a stratified layer above in which waves propagate. The first physical description of turbulent flows induced by the interactions between planets such as tides, libration and precession, and the first modeling of the associated dynamos. We have developed a true interdisciplinary approach by collaborating with planet, Earth and space scientists. With Fludyco, results obtained in the lab and confronted by the real world help advance science as a whole.